So let's jump right in, move over to that page. Okay, so the logarithm is defined to be exactly the inverse function to the exponential functions. So you can always think of the logarithm as just an exponent in a different equation. So that's probably the best way to do it. So we'll look at evaluating them. We'll only be able to evaluate a select few based on their inputs, but they're a nice tool for solving equations with variables in the exponent. It's maybe like their main utility from an algebraic perspective. So let's, given a b greater than 0, so this is your base, just like in exponential functions, the logarithm with base b is written y equals the log base b of x, and is defined by so y is equal to the log base b of x can be rewritten as the exponential equation b to the y power is equal to x. So let's first look at how we can utilize this to evaluate some logarithmic functions, or logarithms with just numbers in them. So the instructions for this first example are just to evaluate. So let's say we have log base 5 of 25. So if you look at this definition, basically you can evaluate any logarithm by looking at the input and asking what power of the base is equal to the input. So same thing here. Basically, you would be trying to answer 5 to what power let's say equals 25. So in this case, we can answer that question. It's 2. 5 to the second power is 25. So that's what the logarithm evaluates to. There's many where it would be hard, like if you had log base 5 of 7, you're not going to know what that is. Because, you would know it's between 1 and 2, because 5 to the first is 5 and 5 to the second is 25. But to get an exact answer, you're going to need probably a calculator. Okay. Let's look at, say, let's say the log base 4 of 1 over 64. So you'd be asking 4 to what power makes 1 over 64. Now, we know the reciprocal powers come from negative exponents, right? 4 to the negative first would be 1 over 4. 4 to the negative second would be 1 over 16. And then 4 to the negative third would be 1 over 64. So this answer would be negative 3. I don't know why I was writing 1 over 64 again. So this would be negative 3, right? That's because 4 to the negative third equals 1 over 64. So that would answer that question. Again, basically, if you're able to evaluate the logarithms, you're able to relate the base to the input via some sort of exponent. Let's look at, let's say, the log base 7 of 1. This is going to be 0 because 7 to the 0 power equals 1, right? 7 to what power makes 1? 7 to the 0. That would actually be true for any base that's not 0, right? You could have log of 1,000 of 1, log base of 1,000 of 1, and 1,000 to the 0 would still make 1, so that log would evaluate to 0 as well. So if you take a positive number, which is the base, and you raise it to a power, a positive number raised to any power can only come out as a positive value. So for that reason, if you try and do the log of a negative or the log of 0, it's undefined. So the log of log base, I don't know, 18 of negative 18. This, a lot of people might say, oh, -1 or something like that, but this is actually undefined. Right? The log of 0 or any negative number is undefined. So for that reason, we could say the domain of a logarithmic function is going to be the positive real numbers. Okay, so that's generally how you evaluate logarithms. Like I said, there's many of them that we're not going to be able to evaluate just by looking at them, so we will need our calculators. But the bases, there's two that we use way more than any others, and that's known as the common logarithm and the natural logarithm. In algebra, a lot of times they will have you using the common logarithm, which is just the base 10 logarithm. But in calculus, the one that works better with the derivative, which is what we're going to be studying this semester, is the natural logarithm. So we're mostly going to be using the natural logarithm exclusively in calculus. But I will make note of both of the notations. So the two most used logarithms are written with their bases understood. So the first of which is the common logarithm. And that's just written as log with no base. So if you see something that looks like just log of x or log of some number, that you mean that the base is 10. Even though you don't have a subscripted number anywhere, so to evaluate any of these, you'd be saying 10 to what power makes x. The natural logarithm has base e, Euler's number that we talked about last class with exponential functions. So this is written y equals ln of x. So that's the natural log of x. And this means base e. So let's evaluate some using these notations. Again, basically, common logs we're only going to be able to evaluate if we recognize them as a power of 10, and natural logs we're only going to be able to evaluate if we recognize them as a power of e. So let's evaluate a few. So I meant to write example there, and I wrote evaluate. So let's say we have the log of 1,000. 10 to what power makes 1,000? Powers of 10s are easy because basically you're just counting zeros. So 10 to the third power would make 1,000. So this is 3. Let's say we had maybe part B. Let's say we were doing the natural log of the cube root of e. Well, we know we can rewrite the cube root of e as e to the 1/3 power. So e to the 1/3 power makes e to the 1/3 power. I know that sounds like self-evident, but that's how you think about evaluating these logs. So another property really is if you can rewrite it as e to a power, it kind of cancels with that base and you just get the exponent. C, maybe we would do the natural log of 1 just to reinforce what we said before, but we know this is going to be 0 because any number to the 0 power is going to give you 1. And then D, maybe we do the common logarithm of 1 over 100. Well, we know 100 is 10 squared, so if you're doing an reciprocal of that, this would be a negative value. So this would be -2. 10 to the negative second power is 1 over 100. Okay, similar to exponential graphs, there will be two distinct graphs of logarithms. So they have two shapes, and it's again based on the base. So it's gonna evaluate the same way it did. You're gonna have two graphs, one for when the base is between 0 and 1, and one for when the base is greater than 1. So the graphs of logarithms. So we're graphing something of the form y equals log base b of x. So the first graph would look something like this. So this is when b is greater than 1. Your base is greater than 1, so I don't know. So for example, you might have y equals the log base 2 of x. The other ones we talked about, the common log and the natural log, would both fall in this category. They would have a base of about 2.718 for the natural log and 10 for the common log. If you have a base between 0 and 1, you're going to get a picture that's a little bit different. It's going to go to negative infinity as you move to the right rather than positive infinity. So this is a base between 0 and 1. So you might have y equals the log base 1/2 of x. And you can take your time and set up some ordered pairs and actually plot these, but we'll just plot a few in Desmos to point out some things and make chat. There's no, okay, good. Okay, so let's go ahead and look at, let's say y equals, just to confirm, y equals log base 2 of x. We're getting that graph we talked about. And if you would do y equals the log base 1/2 of x, get that graph. So you see the two shapes that we talked about appear right there. But let me point something else out. Remember, the logarithm is really the reverse process of finding an exponent. So if you remember from algebra, a function and its inverse function are related how? Well, they're exactly the flip about the diagonal line y equals x. So what should be the inverse function of y equals log base 2 of x? The inverse function would be y equals 2 raised to the x power. And notice that if you put y equals x up there, it is exactly a reflection of those two graphs. So that's why those would be inverse functions. So if you would plug 2 to any power in where x is in log base 2 of x, you would just get the exponent back. So if you compose the functions with each other, they just fall back on the line, y equals x. And it would be the same with, let's do it maybe for 1/2 x. It didn't make it in the base. 5. Let's change this now. Instead of 2 to the x, let's make it 0.5 to the x, or 1/2 to the x, same thing. Notice this is still quite the reflection, even though there's some overlap there. That's just because the two graphs intersect each other, whereas if you look at y equals log base 2 of x and y equals 2 raised to the x, those graphs do not actually intersect. So let's continue. Let's start looking at some of the properties of logarithms, and that's where we use them for solving equations. So for each, I will remind you that each of these properties of logs comes from one of the exponential rules. And if you wanted to prove why they're true, you would actually use the exponential rules. I'm not going to go through all the proofs, but I'm just going to remind you because it's always good to rehash the rules from other functions that are related. So if you have something like the log of m, and this would go for any base log so long as the base is matched, but I'm just going to write the properties using common log. But so long as the bases match, this will transfer to any log. I just don't want to write this subscript b all the time. So let's say the log of capital M plus the log of capital N. This would be the log of m times n. So it takes that product of sums there. And this is actually related to the rule a to the m times a to the n is a to the m plus n. Second, if this changes to subtraction, then you might guess that this is going to be the quotient, which is exactly what happens. The log of m minus the log of n becomes the log of m over n. And this is related to a similar rule. A to the m over a to the n is a to the m minus n. And then the most useful rule for solving equations, if you have the log of m to the p power, you can actually bring that power down outside as multiplication. So if you have a variable and an exponent, you can usually take logs of both sides of an equation and bring that exponent down. And then you can rely on your arithmetic skills to solve the remaining equation. This one is actually, if you have a to the m raised to the n, then you multiply those exponents, a to the m times n. Okay, we also have some inverse properties. So you may have already kind of guessed those from evaluating the logs that we've looked at so far, but if you haven't, I will point them out explicitly. One is if you have the log base b of b to the x, this is equal to x. And the second, if you have b raised to the log base b of x, this is equal to x, but only for x that are positive, because again, in terms of order of operations, you would have to evaluate the exponent first in property 2. And the logarithm has a domain of only positive values. So x can only be positive there. Whereas in number 1, b to the x would happen first in order of operations, and b to the x would always be a positive number. So you'll never have a bad input. In particular, the two we see most common are with the common and natural logarithms. So if you take the natural log of e to the x, this is equal to x. And also if you would do e to the natural log of x, this is equal to x, provided x is positive. And similarly for the common log of 10 to the x is x, and 10 to the log of x is x. Okay, so let's go ahead and see how we use these to solve equations. So I need to point something out. When I was teaching this class, I used to always leave all the logs unevaluated, and students would have a lot more trouble. So for the past several semesters, someone suggested that I just approximate as soon as possible, and that would make the algebra a bit easier. So that's what I've done now. So let's go ahead and solve. So let's say let's say we have 10 equals 3 to the 2x plus 1. See, so we have a exponent that's got an unknown in it. So we wouldn't normally have a way to deal with that in the past, but the logarithm allows us something to do. So let's just go ahead and take log of both sides. So the log of 10 would equal the log of this whole right-hand side, 3 to the 2x plus 1. And, okay, so on the left, we know the log of 10 would just be 1. And on the right, what we can do is we can take that whole exponent in parentheses and write it in front. That's by property number 3 of logarithms. So this is by log property number 3. And then you can go ahead and just put the log of 3 in your calculator. And that comes out to, I rounded to 3 spots, 477. And then you can go ahead and just use the distributive law and go ahead and solve. So if you multiply 2 by 0.477, you get 0.954x plus 0.477. And then we can just go ahead and solve this in 2 steps. It's just a linear equation now. So we just want to subtract the 0.477 on both sides. So we've got 0.523 equal to 0.954x. And then we divide by the 0.954. So that gives us a final answer of about 0.55 is equal to x. So I'll wait a minute for you to catch up on that one and let me know if you have any questions, because I know it probably seems like a lot of steps and really fast, but really we just took log of both sides, brought the 2x plus 1 down using the properties, plugged it into our calculator, and then just distributed. So take a minute, look over those steps, and let me know if you see anything that looks confusing. Okay, I'm just going to check the chat real quick. Don't see any questions yet. So why don't we move on to the next one? It's going to be 5 to the 3 minus 4x equals 7 to the 9 plus x. So it's going to be slightly more complicated. But the same general rules are going to apply. We've got two expressions that both have unknowns in the exponent. So we're just going to take the log on both sides and then bring those expressions down using property number 3. So I take the log of both sides, log of 5 to the 3 minus 4x, and then the log of 7 to the 9 plus x. Bring each of those down, so I've got 3 minus 4x times the log of 5. Then on the right-hand side, I've got 9 plus x times the log of 7. Now what I'm going to do is I'm just going to put the log of 5 and the log of 7 in my calculator and get a approximation. So I've got 3 minus 4x times 0.7. And then I've got 9 plus x times 0.85. So what you want to do now is just distribute on both sides. get your x's on one side and your regular numbers on the other side. And that'll pretty much do it. So we've got 2.1 minus 2.8x on the left, multiplying the 0.7 through. Now we want to multiply the 0.85 through. So 0.85 times 9 gives 7.65. And then we've got plus 0.85x. So I want to move my x's to the right. So that can be done by adding 2.8x on both sides. And I want to move my regular numbers, namely my 7.65, on the left-hand side. So I'm going to subtract 7.65. So kind of doing those two steps at once leaves me with minus 5.55, and that equals 3.65x. So then to solve, that's all we need to do is divide by 3.65 to get the x by itself. And that leaves us with about minus 1.52 as our value for x. So again, take a look and let me know if anything looks confusing there. I know it seems like a lot of steps, but it's really not so bad. So what we'll do next is we'll actually look at some examples where we have variables, unknowns inside the input of a logarithm, and we want to solve those equations. So when we do that, we'll be using the inverse properties, because to undo a logarithm, basically you're going to have to exponentiate with a matching base. Okay, so hopefully you've had enough time to look at this. Any questions in the chat? Don't see any. Okay, so let's go ahead and move on. Let's look at some of these other examples I talked about. So we want to solve for x. So A, let's say we have the log of 5x minus 1 equals 2. So that 5x minus 1 is a problem because it's an input of the logarithm. So the only way we're going to be able to get that out is by using the inverse property number 2. So we're going to make both sides the exponent of 10, because if these are equal, then if you make them the same exponent of 10, that will also be an equality. So if I do 10 raised to the log of 5x minus 1, that'll be the same thing as 10 to the second power, right? And then on the left-hand side, we get cancellation. That was our second inverse property. So that is 5x minus 1, and the right-hand side is 100. So this is by inverse property number 2. So this is a pretty easy equation to solve. Just add 1 and divide by 5. So we get x is 101 over 5. All right, and then for part B, let's say we have the natural log of 7x plus 3 equals 0. Now we're going to do the same thing here, but now the base should not be 10. We need to exponentiate both sides with base e, because that is what cancels with the natural log. So e to the 7x plus 3 is equal to e to the 0. The left side just cancels by that same property, and e to the 0 is just 1. And then we can solve this by subtracting 3 and dividing by 7. 1 minus 3 is -2. So this will be -2 over 7. So how are those first two? Did they make sense?
Yeah. Yep.
Okay, good. So let me show you a third problem I kind of came up with on my own. It's not from the exercises or anything, but it highlights why parentheses matter in terms of where an exponent is with a logarithm. So check this problem out. If we have the natural log of x squared equal to the natural log of x squared. So notice these are two different expressions, but a lot of times you'll see students not care about where they write the exponent, but they're different things. The left-hand side is the natural log of x times the natural log of x. The right-hand side is the natural log of x times x. That's what x squared means, right? If you think about it, this is really natural log of x times natural log of x, whereas this one is natural log of x times x. So they're different things, but they actually agree at a couple of spots. So in order to solve this one, one of the main things this thing is highlighting is that we can only use property 3 on one of the two. And we can only use property number 3 where we bring the exponent to the outside on the right-hand side of this equation. It does not apply to the left-hand side. So essentially I can write this as the natural log of x squared, and then this will equal 2 times the natural log of x. So this is by log property number 3. And then what you can do is you can subtract 2 natural log of x from both sides to try and get everybody on one side. Right, so then I have the natural log of x squared minus 2 natural log of x equals 0. Well, what has that accomplished? It's actually given me something that I can factor, right? If you think about y squared minus 2y, this could factor into y times y minus 2. But I don't have capital Y in common. I actually have natural log of x this time. So y is like the natural log of x. So I can write the natural log of x times the quantity natural log of x minus 2 equals 0. And now I have two things that multiply to 0, the natural log of x and natural log of x minus 2. So from the zero product principle, one of those has to be 0. So either the natural log of x is equal to 0, or the natural log of x minus 2 equals 0. So how do we solve this? Remember, we essentially, and let me skip one step. Natural log of x minus 2 equals 0. That would be the same thing as the natural log of x equals 2. That's the only way the second set of parentheses would be 0. So to solve these equations, we would again use inverse property number 2. So we would have e to the natural log of x equals e to the 0, or e to the natural log of x equals e squared. So we get our two answers, x equals 1 or x equals e squared. And that is by inverse property number 2 again. So it's a harder problem. I would not normally ask something like that, but I like it because it shows a lot of properties of both logarithms, inverse, and it includes some factoring as well. and we just looked over factoring last week. So yeah, if you can wrap your head around that problem, that would be a good thing. But again, that's probably harder than a question you'd typically be asked. So let's go ahead and look at a word problem, and then we're probably actually at the end of the section. So then you'll just have some extra time to work on the homework, and then Friday we'll take a look at any homework questions you might have. Go over maybe a handful. So let's suppose we have something that's modeling a population. P of t equals 437.2 times 1.036 to the t, and this is modeling the population of a county and thousands of people. T years since 1995. When will the population reach 1 million? So again, P of t is what's standing for a population. So essentially, we want to set P of t equal to something. One thing to watch, though, is notice that this is in thousands of people. So we're not going to set P of t equal to 1 million, right? It needs to be a certain number of thousands. And 1 million is 1,000 thousands. Does that make sense? So because 1 million is 1,000 thousands, we're actually going to set the P of t equal to 1,000. And then we're going to solve. So you always have to pay attention to your units when you deal with these problems. A lot of times you're handed some data or a model, and someone else came up with the units, and it might not be the same choice you would have chosen, but you still have to be able to work within the confines of that system. So again, we've set that P of t equal to 1,000, and we've got our model. I reversed the what goes where, but it's the same, right? The equality symbol is reflexive. So we want to get this exponential guy on its own, so we're going to start by dividing by 437.2 on both sides. So we end up with this 1.036 raised to the t is equal to 2.28728. And then what we want to do is just take the log of both sides and solve. So you can choose whatever log you want. It doesn't really matter. It's just going to change which button you're pressing on your calculator at the end. I'm going to use the natural log because it's one less letter to write. And, we're mostly going to be using natural log in the future. So it's a good habit to just start using natural log. So then we bring the t to the outside from that property number 3. And you could do the natural log of 1.03. You could do both of these in your calculator and get approximations here. I'm just going to leave them as is because I know t is the only variable. This natural log of 1.036 is a number, so you're just dividing by that thing really on both sides, and then that's what you punch into your calculator at the end there to get the final answer. So we end up with t. This is 23.4, but that's not much of an answer to the question. Let's again think about the original variables. So we know the answer is 23.4 when we put it in, but they're asking when will the population reach? Notice T is years since 1995. So let's say 1995 plus 23 would be 2018, and 1995 plus 24 would be 2019. So basically the population of the county will reach 1 million between, let's say, 2018 and 2019. And again, that's because their input is based on years since 1995. So if you get an answer and you add it to 1995, or add it to 1995, that'll give you the actual year that they're talking about. So again, I'll scroll up a little bit. Please let me know, do you have any questions on the steps there? It was actually easier than the previous log questions we had been fielding in terms of difficulty. Okay. So I'll end the recording here.